72 hours ago, the last of Mars's orbiters finished transmitting data on a visitor that was never meant to come this close. The object known as 3I-ATLAS, only the third confirmed interstellar body ever observed, has now left Mars's gravitational influence, and its path is bending inward toward the Sunday. The math is clear, and deeply unsettling. If the current models hold, its closest approach to Earth will occur in less than 4 months. For weeks, space agencies assured the world that 3I-ATLAS was nothing more than a frozen relic, a silent traveller passing harmlessly through. But the latest tracking updates from ESA's ExoMars Trace Gas Orbiter and NASA's Deep Space Network revealed something no one expected: a gentle but continuous deceleration of about 0.003 meters per second squared. It's a value so small that most people would overlook it, yet to orbital physicists it changes everything. Tonight, we follow the story of how an object once believed to be leaving the solar system has instead begun turning inward. We'll uncover what Mars's orbiters actually saw, what the spectrometers detected inside its coma, and why several agencies have quietly shifted their status from observation to contingency tracking. If you're listening from somewhere dark and quiet, step outside for a moment and look east before sunrise. Somewhere beyond that faint orange glow, an interstellar traveller is changing course. Whether it's the result of natural physics or deliberate control, that's what we're here to find out. Before we begin, make sure to subscribe, tell me where you're listening from and what time it is there, and share this episode with anyone who still believes the solar system is predictable. Tonight, it might not be. For months, 3I-ATLAS followed a path that seemed to obey the most predictable laws of celestial mechanics. It entered our solar system on a hyperbolic course, fast, distant, and destined to leave forever. Its inbound velocity, nearly 67 kilometers per second, made it one of the fastest interstellar visitors ever detected. By all accounts, it should have skimmed past Mars, curved slightly under the sun's gravity, and then vanished into the deep again. But that's not what happened. In late September 2025, analysts at the European Space Operations Centre in Darmstadt noticed something that didn't fit. The data coming from ExoMars Trace Gas Orbiter, combined with signals from NASA's Deep Space Network, showed a minute but consistent shift in the object's motion. The orbit wasn't bending as expected. A deviation of 0.02 degrees, almost invisible, had appeared in the models. For ordinary objects, that kind of change would mean nothing. For an interstellar body travelling at tens of kilometers per second, it was enormous. At first, everyone assumed it was a calculation error. Solar wind variations, sensor noise, even gravitational interference from Mars's moons. All plausible explanations. But cross-checking from independent tracking stations confirmed the same anomaly. 3I-ATLAS was slowing down. Not abruptly, not like an impact or a burst of gas, but gradually. A smooth, steady deceleration measured at 0.003 meters per second squared. That number might sound trivial, but space doesn't tolerate coincidences. A comet losing speed implies a force, and every force needs a cause. The most likely candidate was outgassing, the process by which a comet's frozen surface sublimates and releases jets of vapor, pushing it in unpredictable directions. The problem was that 3I-ATLAS wasn't near enough to the Sun to outgas that strongly, and its coma, the gas cloud around it, showed no signs of activity at all. At Darmstadt, the data teams began running simulations. They modelled hundreds of scenarios, from gravitational assists to thermal stress reactions. None of them reproduced the pattern observed. The deceleration vector didn't align with sunlight, solar wind, or any known thrust direction. It was angled 17 degrees inward, toward the Sun-Earth line, as if something were deliberately correcting its course. For the first time, the term controlled motion appeared in internal documents, not in press releases, not in scientific papers, just quiet memos between mission directors. Some dismissed the phrasing as dramatic, others weren't so sure. If this had been a natural event, the slowdown should have shown variations, small fluctuations as jets of gas opened and closed. But the numbers were frighteningly precise. Every 12 hours, the velocity decreased by the same fractional amount, as though it were following a program, not physics. Astronomer Lena Bourdon at the University of Cambridge described it best. It behaves as if it's performing a gravitational capture maneuver in reverse. In simpler terms, a controlled deceleration. time to remain within the sun's sphere of influence instead of escaping it. The implication was staggering. A random rock from interstellar space shouldn't know how to stay. Yet, if the models were right, by altering its velocity just slightly near Mars, 3I-ATLAS had shifted from a hyperbolic path to a bound orbit, a course that would bring it closer to the inner planets and eventually toward Earth's vicinity. The global astronomy network went into quiet overdrive. Observatories were asked to retarget. The Goldstone radar extended its operating schedule. And somewhere deep inside NASA's coordination logs, the object's classification changed. It was no longer tagged as a non-returning visitor. It now read, "Temporary solar capture, pending verification." To the public, nothing had changed. But within mission control rooms across 3 continents, the tone did. Engineers stopped speaking in past tense. The question was no longer where 3I-ATLAS had come from, it was where it was going next. And as its signal drifted inward, faint but unmistakable, one unsettling truth began to sink in. The universe had just rewritten one of its simplest rules. Something that should have left forever had, somehow, decided to stay. When 3I-ATLAS crossed Mars's orbit, it marked a rare moment in astronomical history. 7 spacecraft from 4 different space agencies were watching the same target, at the same time, from multiple angles. The conditions were perfect. Instruments were ready. Cameras were primed. The scientific community expected an unprecedented cascade of data. High-resolution imagery, spectroscopic readings, particle samples from the solar wind. And then, nothing. No live feeds, no press releases, no raw data uploads, just silence. On October 4th, 2025, the European Space Agency confirmed the final transmission from its ExoMars Trace Gas Orbiter. The images, captured between October 1st and 3rd, showed a single bright speck moving across a starfield, the official identification marker for 3I-ATLAS. But after that final file, the communication logs stopped. When asked why, ESA's media office issued a vague statement about data verification and calibration delays. That might have satisfied casual observers, but not the scientists who knew how quickly Mars data usually becomes public. Ordinarily, missions like Mars Express release preliminary images within 48 hours of acquisition. NASA's Mars Reconnaissance Orbiter uploads its raw shots daily. Even China's Tianwen-1, typically more reserved, publishes major findings within a week. Yet, for this event, the closest interstellar encounter in history, the data pipeline went completely dark. Inside mission control centers, engineers kept working, but access levels changed overnight. Researchers who'd been processing open-source telemetry suddenly found their credentials revoked. Direct communication between the ESA and NASA science teams was suspended pending review. At first, it felt like bureaucracy. By the 3rd day, it felt like containment. Rumors began to circulate first in encrypted forums, then among independent astronomers. Someone within ESA allegedly described an abnormal reflective pattern in the Mars data, something inconsistent with ordinary cometary material. A Chinese astrophysicist reportedly hinted that Tianwen-1 had captured electromagnetic fluctuations not attributable to plasma interactions. And one anonymous engineer from the Jet Propulsion Laboratory in Pasadena wrote a single line in an internal chat before vanishing from project discussions entirely. "We found something, but I don't think we should show it yet." It's easy to dismiss stories like these as fiction, but the timeline itself raises questions. Between October 2nd and 7th, the exact window of the Mars flyby, not one of the 7 active Mars orbiters released public data. That's never happened before. Even during solar conjunctions, when signals are disrupted by the sun, agencies usually coordinate updates. This time, there was no coordination, no excuses, just silence. What's stranger still is that the silence seemed synchronized. Around the same hour ESA paused its Mars uploads, NASA's Deep Space Network began reporting maintenance delays. China's planetary imaging site went offline for technical optimization. The UAE's Hope orbiter, which routinely shares public updates, simply stopped posting altogether. 4 agencies, 4 unrelated infrastructures, all muted. Amateur astronomers tried to fill the void. A small observatory in Chile caught a faint flash above Mars's limb. A brief, reflected pulse lasting less than half a second. Hours later, a spike appeared in the X-band radio frequency, recorded by an independent station in Australia. The timing matched perfectly with the last confirmed position of 3I-ATLAS. Coincidence? Perhaps. But coincidences rarely demand silence. By mid-October, scientists at ESA stopped responding to inquiries entirely. The official line remained the same: calibration delays. But behind closed doors, something had changed. Tracking antennas across Europe were reoriented not outward, as if chasing a retreating object, but inward toward the inner solar system. The target trajectory files, once labelled outbound object, were renamed inbound priority. This to stock, somewhere between Mars and the Sun. 3I-ATLAS had done something it shouldn't have been able to do, and the instruments on Mars had seen it happen. The data exists locked inside encrypted servers in Darmstadt, Pasadena, Beijing, and Dubai. It's been processed, reviewed, and likely compared against every known natural explanation. But until the agencies decide what the public can handle, that data will remain where it is, silent. Mars saw something. And whatever it was enough to make every space agency on Earth stop talking at once. For days after the Mars encounter, 3I-ATLAS appeared to behave exactly as expected. A frozen body from another star system, passing briefly through ours before vanishing into interstellar night. Its outbound trajectory had been calculated, plotted, and confirmed by at least a dozen observatories. Everything seemed stable. Everything seemed normal. Then, it began to slow down. At first, the change was so subtle that it took several rounds of cross-checking to confirm. When engineers at the European Space Operations Centre reprocessed the post-flyby telemetry, they found that 3I-ATLAS's velocity had dropped by a fraction so small it barely registered. Yet, over the next 48 hours, that fraction held steady, and then it deepened. By October 6th, the deceleration measured 0.003 meters per second squared. That may sound like nothing, barely the pressure of a human breath, but in the frictionless vacuum of space, even a thousandth of that is significant. For an interstellar object moving at tens of kilometers per second, that kind of drag doesn't happen naturally. The first theory proposed was simple: outgassing. As a comet nears the Sun, frozen volatiles sublimate into gas, producing jets that can push against the nucleus and alter its motion. But outgassing creates random chaotic thrusts, never this smooth, never this consistent. And 3I-ATLAS wasn't close enough to the Sun for such activity anyway. No visible tail, no plume, no coma expansion. The object's luminosity remained flat. If it wasn't gas, then what was slowing it down? NASA's Jet Propulsion Laboratory began comparing the readings from the Mars Reconnaissance Orbiter and Odyssey, searching for any thermal anomaly. None appeared. The surface temperature remained too cold to produce jet activity. ESA's Mars Express team suggested that dust or solar wind pressure could be acting as a brake, but again, the math didn't fit. The deceleration vector didn't line up with sunlight. It was offset tilted roughly 17 degrees toward the Sun-Earth line. That small offset changed everything. If a comet were simply being pushed by solar radiation, the deceleration would always align with the direction of sunlight. A 17-degree angle meant something else was applying force. Something controlled, sustained, and targeted. The trajectory wasn't random drift. It was adjustment. Behind closed doors, ESA scientists began referring to the event as a reverse capture maneuver. The term was borrowed from orbital mechanics, the idea that if you slow down at the right moment, gravity can pull you into a new orbit instead of letting you escape. A spacecraft would do this intentionally to enter a planet's gravitational field. A natural object, however, shouldn't. At Cambridge University, astrophysicist Lena Bourdon ran simulations based on the revised data. Her models showed that if 3I-ATLAS maintained the same rate of deceleration for another 30 days, its hyperbolic path would flatten into an elongated ellipse, no longer a one-time visitor, but a temporary resident of the solar system. That outcome stunned her team. End. 3I-ATLAS wasn't leaving anymore. It was staying. Yet the real mystery wasn't the math, it was the consistency. Every 12 hours, the slowdown repeated in exact intervals. like a pulse. No variation, no drift. As if whatever was generating the braking force was operating on a schedule. The data was shared discreetly with NASA, but only a handful of people saw it before the file was locked under restricted access. By then, whispers had already spread. Engineers monitoring the deep space network claimed that minor frequency fluctuations, tiny modulations in 3I-ATLAS's radar reflections, were matching the timing of the deceleration intervals. One pattern, one rhythm, one motion repeated again and again, across millions of kilometers. By mid-October, mission control teams had stopped referring to 3I-ATLAS as a comet altogether. The language changed. Object, body, mass, target. Neutral, vague, deliberately unspecific. The word natural disappeared from internal memos entirely. Something was pushing against 3I-ATLAS gently, deliberately, without any visible source. No flare, no heat, no chemical discharge, just motion, as if it was being guided by invisible hands. The slowing continued, constant and controlled, and as Earth rotated beneath the silent night sky, telescopes across the world began tracking a visitor that was no longer on a path to leave. Whatever 3I-ATLAS was, it had changed its mind. When the first spectral data from 3I-ATLAS arrived, scientists expected a familiar pattern, the signature of a comet. Frozen water, carbon dioxide, maybe traces of methane and dust. Spectroscopy is supposed to tell a simple story. Each molecule absorbs and emits light at specific wavelengths, creating a barcode of chemistry that scientists can instantly recognize. But when the readings came in from ExoMars's Nomad spectrometer, the pattern didn't make sense. The data wasn't chaotic or noisy. It was too clean. Instead of the tangled web of overlapping absorption lines typical of natural materials, the instrument recorded a sequence of narrow, evenly spaced peaks. At first, researchers thought the instrument had malfunctioned. The ExoMars camera wasn't designed to observe something 30 million kilometers away, and its detectors could easily misinterpret scattered sunlight. But when ESA's Mars Express orbiter used its Omega instrument to take follow-up readings, the same pattern appeared again, identical, precise, unmistakable. At wavelengths of 3.29 and 3.46 microns, sharp emissions cut across the spectrum like laser lines. These frequencies are sometimes associated with hydrocarbons, but never with such symmetry. They repeated at fixed intervals, almost as though the source was modulating its own light. In spectroscopy, natural features are messy broad bands smeared by temperature, rotation, and motion. This was geometric, deliberate. By October 8th, ESA had quietly flagged the dataset for restricted review. Only a handful of scientists were allowed access, and they were instructed not to share images or raw numbers outside internal servers. Among them was Dr. Marianne Elson, a French astrophysicist working in Toulouse, who later admitted to colleagues that she had never seen anything like it. "These are not emissions," she reportedly said during a closed session. "They're instructions." That quote never appeared in public documents, but its echo spread through the small community of planetary spectroscopists. At the Jet Propulsion Laboratory in Pasadena, analysts attempted to recreate the pattern using computer simulations. They mixed known elements, added plasma effects, tested temperature extremes, and even modeled electrical discharges along magnetic fields. None produced the result. The spectral spacing remained mathematically exact, so perfect it could be plotted as a harmonic sequence. Then came another discovery. When the data was compared to earlier ground-based spectra taken by the Very Large Telescope in Chile, subtle fluctuations in brightness revealed a repeating interval, a periodicity of 16 minutes between intensity peaks. The pattern wasn't random. It cycled bright dim, every 960 seconds. Natural comets don't behave that way. Outgassing is chaotic. Surface activity is noisy. Nothing repeats with metronomic precision unless something controls it. NASA and ESA convened a joint conference call on October 10th to discuss the anomaly. According to leaked summaries, 3 possibilities were debated. The first, an unknown molecular compound with reflective symmetry. The second, a sensor crosstalk issue between instruments. The third, the one nobody wanted to say aloud, that 3I-ATLAS might be emitting coherent light. Coherent emission means energy released in phase, the principle behind lasers. No natural body has ever shown that property. If 3I-ATLAS was producing such emissions, it meant the light was being organized. Publicly, ESA issued a bland statement that spectroscopic data is still under calibration. Privately, the data logs were encrypted and pulled from public archives. Even internal staff had to request clearance to view them. By mid-October, new readings from the Perseverance rover's upward-facing Skycam detected faint infrared pulses reflected through the thin Martian atmosphere. They matched the same 16-minute cycle seen in orbit. It was now clear that whatever was happening wasn't an instrumental glitch. It was radiating outward. A few scientists suggested exotic physics. Stimulated Raman scattering, photonic crystal resonance, even plasma lensing near the comet's surface. But none could explain the clean harmonic intervals or why the emissions came and went with such precision. To those who saw the full data set, one thought became impossible to ignore: the light. From 3I-ATLAS wasn't simply reflecting the Sunday. It was responding to it. Every pulse seemed to correspond to small fluctuations in solar flux, as if the object were sampling or synchronizing with the sun's rhythm. That synchronization is what made some scientists shiver. It meant intent, or at least reaction. Since then, no new spectra from 3I-ATLAS have been released. The official explanation remains signal interference, but the data exists, stored, encrypted, and analyzed behind closed doors. And those who've seen the original graphs describe them not as random or chaotic, but as structured like a language written in light, one that no one on Earth yet knows how to read. The spectra of 3I-ATLAS don't match anything in nature. And perhaps that's because they weren't meant to. At first, the lack of communication between space agencies seemed procedural, the kind of bureaucratic delay that happens when too many organizations share the same sky. ESA had its protocols, NASA had its chain of command, and China and the UAE kept their data behind national firewalls. But as days passed after the Mars flyby, it became clear that this was no delay. It was coordination. On October 8th, 2025, a fragment of telemetry appeared briefly on a public server operated by an Italian university before being taken down within hours. The file, tagged with metadata from the Mars Reconnaissance Orbiter, showed 3 narrowband radio spikes, evenly spaced, each lasting precisely 42 seconds, detected during 3I-ATLAS's occultation behind Mars. The pattern didn't look like cosmic noise or static. It looked like a signal. 2 hours later, the same sequence appeared in logs from ESA's Cebreros ground station in Spain. Then again, from the Beijing Aerospace Control Center. 3 agencies, 3 recordings, all matching perfectly time-synced to within a fraction of a second. But none of them publicly acknowledged it. Instead, internal documents were quietly updated with a new label: Anomaly Type 3, pending interagency coordination. Type 3 anomalies are normally reserved for biological contamination events or spacecraft emergencies, never radio data. That night, the NASA Deep Space Network abruptly went into restricted mode. Access to raw signal feeds was revoked. China's Tianwen-1 database went offline for scheduled maintenance. ESA's Mars Express team received an internal notice to suspend external data sharing until further review. 4 continents, 1 decision. Inside control rooms, confusion turned to unease. Engineers who reviewed the captured spikes said the frequency fell within 8.4 GHz, a common band for deep space communications. That's the same range used by spacecraft to exchange telemetry and commands. In theory, 3I-ATLAS had no transmitter, yet something in that frequency band was active, repeating with mechanical precision and growing slightly stronger with each pass. A leaked summary from ESA described it cautiously: periodic emission, consistent with intentional modulation or reflection. The difference between modulation and reflection is enormous. Reflection means it's bouncing radio waves back. Modulation means it's encoding information in them. When the anomaly was cross-checked against NASA's radar logs, analysts noticed something else. The delay between the spikes varied slightly by milliseconds in a pattern that looked deliberate, like binary spacing. Even a few within the agency began calling it the Mars handshake. By October 10th, the global science network had fractured into silence. Ordinary researchers, those used to accessing open telemetry, found their logins invalid. Internal messaging systems between ESA, NASA, and JPL were rerouted through encrypted channels. At least one scientist at the Canberra Deep Space Communications Complex claimed his system automatically reoriented toward 3I-ATLAS without manual input. The system log showed the command had been triggered by an external ping. When questioned, NASA's press office called it a software glitch, but technicians who reviewed the antenna data said the glitch forced the dish to lock on to a moving target more precisely than any automated routine they'd seen. The antennas weren't chasing interference, they were tracking something broadcasting back. Behind the scenes, the four agencies convened a private video call to align their statements. ESA pushed for a cautious explanation, an echo caused by overlapping transmissions. NASA argued for solar interference. China refused to confirm whether it had detected anything at all. The meeting ended with no consensus and no public statement. Days later, the Deep Space Network quietly shifted several antennas to standby mode, citing hardware recalibration. But in classified tracking logs, those same dishes were tagged as listening nodes. Each was assigned the same target name, Object 3I-2025. A 1. Active source suspicion. No one outside the agencies has seen the raw signal data since. Amateur astronomers monitoring deep space frequencies still report faint, repeating pulses every few hours, consistent with the original 42-second spacing. None have decoded them. Officially, the anomaly was caused by instrument interference. Unofficially, insiders whisper that something between Mars and the Sun responded to us not once, but repeatedly, across multiple channels. The signals may have been weak, faint, and fleeting, but to those who saw them before they were buried, one detail stood out. The timing of each pulse mirrored the 16-minute light cycles recorded in 3I-ATLAS's spectra. 2 anomalies, 2 patterns, 1 rhythm, and across 4 continents, every agency that heard it decided to do the same thing: stop talking. Inside the European Space Operations Center in Darmstadt, Germany, there's a server room that few people are allowed to enter. It's a sealed environment, temperature-controlled, shielded against electromagnetic interference, and guarded around the clock. That's where all mission data from ESA's Mars orbiters is stored: raw telemetry, uncompressed images, and spectroscopic archives. Every byte of information about 3I-ATLAS passed through that room, and according to several people who worked there in October 2025, that's also where the data stopped moving. On October 11th, 4 days after ESA's public release of the fuzzy white dot image, engineers noticed that all incoming data packets labelled 3I divided by 2025. A 1 had been automatically redirected to an offline repository. The usual pipelines, the ones that transfer files to ESA's open access portal in Nordwijk, had been disabled. Instead, the data was routed to a closed directory, with restricted clearance known internally as Vault 9. In 20 years of operations, Vault 9 had only been used twice. Once during the Rosetta mission, and once for a classified experiment under NATO jurisdiction. When questioned, the data managers said they were following an instruction from ESA headquarters in Paris. The official reason was to verify signal integrity. But to those inside Darmstadt, it was clear something unusual had been found. Something they didn't want, mirrored across public servers. That night, several researchers working on the Mars Express imaging team received sudden lockouts from their workstations. One scientist, who spoke under condition of anonymity, said the internal database simply displayed a blank message: access suspended, ongoing security review. A few hours later, even the intranet discussion boards vanished, replaced by maintenance notifications. For a facility that runs 24 hours a day, such a blackout was unprecedented. The next morning, an emergency meeting was called in Conference Room B. Only senior analysts and mission controllers were invited. Everyone else was told to work from home. No minutes of that meeting were ever published. But afterward, several engineers noticed a new badge protocol at the security doors. Access to the data network now required dual authentication, 1 personal code, and 1 rotating clearance key issued by headquarters. For the next 3 days, Darmstadt functioned in total information isolation. External connections to NASA, CNES, and the Italian Space Agency were cut. No external researchers could download telemetry. Even email attachments containing the word Atlas were flagged by automated filters and removed from outgoing mail. Meanwhile, in the cafeteria, whispers spread fast. Someone claimed that the ExoMars Nomad instrument had recorded fluctuations in the ultraviolet spectrum that repeated in 16-minute cycles the same period that had been seen in the earlier infrared data. Another rumor said that a small subset of files contained short-range radar reflections showing a structured surface, with periodic ridges too symmetrical to be random. No one could verify any of it, because no one could see the files anymore. One technician later revealed that the file sizes themselves were strange. Normally, raw spectroscopic data from ExoMars averaged between 200 and 400 megabytes per set. The 3I-ATLAS packets were 10 times larger. It was like they contained hidden sublayers, he said, as if something was embedding extra data into the signal. By October 14th, a delegation from Paris had arrived. Among them were security contractors, not scientists. They oversaw the transfer of the locked data from Vault 9 onto encrypted solid-state drives. Each drive was labelled with a red tag reading Class E External Review Pending. The drives were physically removed from the premises that afternoon. No one ever confirmed where they went. 2 days later, a public statement from ESA claimed that the ExoMars data archive had experienced temporary storage instability and would be restored once integrity checks are complete. But the restoration never happened. Even today, the 3I-ATLAS files from October 3rd through October 10th remain missing from ESA's public data catalogue. In the weeks that followed, several staff members were reassigned to unrelated projects. One left the agency entirely. Another, a data systems engineer, quietly told a journalist friend that what bothered him most wasn't what was in the files, it was the pattern of how they were handled. "You don't isolate data like that unless you're afraid of what people will find," he said. And if they were that afraid, it means someone already did. Somewhere, deep within ESA's internal archives, the raw observations from Mars still exist uncompressed, unaltered, and unseen. The data that captured the first close encounter between humanity's machines and an interstellar object remains locked away in silence. And inside that silence, scientists whisper, might be the answer to why 3I-ATLAS slowed down and why, against all odds, it seems to be heading directly toward us. In the desert of California, just outside Barstow, the Goldstone Deep Space Communications Complex sits surrounded by silence. It's one of NASA's most critical listening stations, a place where enormous dish antennas capture whispers from spacecraft millions of kilometers away. On the night of October 12th, 2025, Goldstone was tracking a routine telemetry relay from Mars orbit when an unexpected signal appeared. It was faint, brief, but precise enough to stop the night crew mid-shift. The anomaly came through the 8.4 GHz band, the same frequency used by Mars orbiters for downlink transmissions. But the source wasn't Mars. The timing of the return, the delay between emission and reception matched the known distance to 3I-ATLAS within a margin of 0.04%. The staff assumed it was an echo, the outgoing Mars transmission bouncing off the comet's surface. Goldstone had picked up natural reflections before, from asteroids and even the moon. But this one was different. The signal didn't fade. It replied. Technician Sarah Villanueva, one of the operators on duty, later described the moment in her log entry. It's not a passive reflection. It's phase-locked like it's tracking us. When the team analysed the waveform, they found something remarkable. Natural reflections scatter radio waves randomly, smearing them across a broad frequency range. The return from 3I-ATLAS was narrowband, coherent, and perfectly aligned with the outgoing signal, as if the source had adjusted itself to maintain contact. The first test was simple. Stop transmitting. The dish went silent for 2 minutes. Yet, 20 seconds after the transmission ended, the echo repeated same frequency, same pulse width, but originating from 3I-ATLAS's last known position, not Mars. The object was now re-emitting the signal on its own. At that moment, the night crew initiated what's known as a delay Doppler ping, a standard radar method for measuring distance and velocity. The expected result should have been a clean slope correlating to the object's motion. Instead, the graph came back jagged, segmented into uniform bands, spaced exactly 42 seconds apart. It was the same interval recorded by the European and Chinese networks days earlier. The lost signals had returned, and this time, there was no ambiguity. Goldstone had confirmed them. Within hours, the data was sent to the Jet Propulsion Laboratory in Pasadena for analysis. Engineers there were initially skeptical. Echo anomalies are common when multiple transmitters interfere. But when they ran a cross-correlation between Goldstone's logs and ESA's Cebreros data from October 8th, the timestamps matched perfectly. 3 separate stations, on 3 continents, had recorded the same repeating sequence, phase-aligned, frequency-locked, and originating from a moving object 20 million kilometers away. At JPL, the anomaly was given a name. Event Echo 3, I divided by 12. Officially, it was categorized as a non-random reflection with harmonic periodicity. Unofficially, technicians started calling it the handshake. The data was rechecked, cleaned, and reviewed again. It held. The object wasn't just reflecting signals, it was amplifying and retransmitting them with mathematical precision. By dawn, the situation had escalated beyond Goldstone. NASA's Deep Space Network Management authorized continuous tracking using all 3 major antennas, Goldstone in California, Madrid in Spain, and Canberra in Australia, to triangulate the source. Over the next 12 hours, all 3 stations recorded the same response pattern. 3 pulses of 42 seconds each, then a pause, then 3 more. The amplitude of the final pulse increased slightly, almost like a confirmation tone. Inside JPL's Mission Operations building, the atmosphere shifted from curiosity to unease. Several engineers suggested the signal could be an active radar transponder, a system embedded in the object itself, possibly recharging through solar exposure. But that raised a deeper question. Who built it, and how had it remained dormant until now? By October 13th, NASA classified the entire dataset. A memo marked confidential DSN priority asset was circulated internally, stating that all outbound transmissions toward Object 3I, divided by 2025, a 1, were to be suspended indefinitely. The reason cited was potential interference with unknown autonomous source. Publicly, NASA said nothing. Privately, the Deep Space Network was told to maintain passive listening. Goldstone's operators were ordered to record everything in continuous loops. Late that same night, a new burst arrived, stronger than before, lasting almost 4 minutes. Analysts decompressed the signal and found a faint amplitude modulation riding on top of it. When plotted, it formed a clean geometric waveform, 6 repeating triangles stacked in sequence. No one could explain it. The shape didn't correspond to any known data encoding or natural resonance pattern, but one of the researchers, a mathematician from JPL's radio sciences team, noticed something unsettling. When converted into a frequency time grid, the triangles aligned perfectly with the orbital periods of Earth, Mars, and Jupiter scaled logarithmically, as if the signal were referencing their relative positions. It wasn't noise, it was geometry. After that night, Goldstone's logs were locked under restricted clearance. Only a few within NASA and ESA ever saw the complete dataset. The official record still lists the event as a probable reflection, but for those who heard it live, it felt unmistakably different. It wasn't a reflection at all. It was a reply. By mid-October 2025, 3I-ATLAS had slipped behind the Sun from Earth's perspective, a region known to astronomers as solar conjunction, where direct observation becomes almost impossible. It's a dangerous window for spacecraft, because the Sun's radiation overwhelms communication channels and blinds optical instruments. Normally, during conjunction, data slows to a trickle, but this time, it didn't just slow, it stopped. At first, it looked routine. On October 15th, ESA's Solar and Heliospheric Observatory captured its last confirmed glimpse of 3I-ATLAS as a faint streak near the solar limb. The following day, the object vanished into the solar glare. ESA announced a temporary suspension of tracking, expecting the signal to reappear within a week once the geometry shifted. Yet, when the days passed, something unexpected began happening. In the data, faint, rhythmic fluctuations across multiple solar instruments, as though something behind the Sun was flickering. The anomalies were first noticed by a graduate researcher at the Royal Observatory of Belgium, monitoring SOHO's LASCO C3 coronagraph images. Every 16 minutes, the same periodicity already linked to the strange spectra from Mars, the digital noise patterns in the solar field changed. The flickers were subtle, buried beneath the glare, but statistically consistent. When overlaid on the sun's brightness curve, the oscillations lined up perfectly with the predicted position of 3I-ATLAS. At the same time, NASA's Parker Solar Probe detected brief magnetic pulses sweeping through the inner heliosphere. They were too localized to be coronal mass ejections, too repetitive to be instrument noise. The pulses matched the same 16-minute interval. Parker's magnetometer team logged them as transient anomalies and moved on. But inside the Heliophysics Science Division, someone made the connection. Every pulse coincided with SOHO's visual flicker. By October 18th, an internal ESA report circulated quietly among partner agencies. Its conclusion was cautious but striking. Possible artificial modulation of sunlight via coherent reflection or emission mechanism associated with Object 3, I divided by 2025. A 1. The phrase coherent reflection stood out. It suggested a controlled process, not random scattering, but something capable of synchronizing with the sun's radiation in measurable intervals. The next day, when the sun was at its peak interference, a new data source came online. The Stereo A spacecraft, orbiting ahead of Earth's path around the Sunday. For 12 hours, its imaging system picked up what analysts later described as phase-timed light gradients. These were flashes of increased luminosity appearing just off the sun's corona, fading and returning with exact regularity. The pattern repeated every 16 minutes, then abruptly ceased. After that, the region went dark again. Scientists debated explanations: solar interference, pixel artifacts, even cosmic rays. But the synchronization across multiple instruments, SOHO, Parker, and Stereo A, made random error nearly impossible. Something was modulating the sunlight from behind the sun's limb. That night, at NASA's Goddard Space Flight Center, a small cross-agency conference call took place. According to someone familiar with the discussion, one participant from ESA made a remark that unsettled the entire room. If this is reflection, it's adaptive. The phase delay changes when we shift our sensors. In simpler terms, whatever was producing the flicker seemed to know it was being observed. Publicly, NASA released a statement downplaying the reports as data compression noise due to the sun's intense radiation, but privately, the Deep Space Network had already been instructed to keep all receivers aimed at the sun's blind zone for extended passive listening. And early the next morning, Goldstone picked up a faint narrowband signal rising just above the background static, a repeating three-tone structure, identical to the pattern recorded earlier, when 3I-ATLAS was still visible. By October 20th, 3I-ATLAS should have reappeared from behind the Sunday. It didn't. Telescopes from Chile to Hawaii searched the sky, expecting to find the familiar trail of a dust plume or a coma flare. Instead, the region where it was predicted to emerge remained empty. The object had vanished from all optical instruments. 2 days later, a new observation arrived from Japan's Hinode Solar Observatory. A brief, localized dimming in the sun's photosphere, too sharp to be solar activity, too structured to be coincidence. The dimming lasted less than a minute, but its profile matched an earlier pattern seen in SOHO's flicker data. Something was still there, just beyond our direct line of sight, something that could manipulate or interrupt sunlight itself. No official agency has ever commented on the event, and no further solar flickers were publicly reported after October 22nd. But within the heliophysics community, the phrase, "the flicker behind the sun," became shorthand for the moment Earth lost visual contact with 3I-ATLAS, and possibly for the moment it decided not to be seen again. By the time 3I-ATLAS disappeared behind the sun, the scientific models that once described its path had fallen apart. Orbital predictions, normally among the most precise calculations in astronomy, no longer agreed. Every new set of measurements contradicted the last. What began as a simple gravitational trajectory became a chaos of numbers no one could make sense of. At NASA's Jet Propulsion Laboratory in Pasadena, teams specializing in celestial mechanics worked around the clock to reconcile the data. Their initial task seemed straightforward: update the post-Mars trajectory using the most recent radar and optical measurements. But when they did, the equations failed. The residuals, the tiny differences between predicted and actual positions, were no longer random. They formed a repeating curve, cycling every 16 minutes, identical to the frequency seen in the light flickers and radio echoes. That kind of periodic error shouldn't exist in orbital math. The motion of celestial bodies follows Kepler's laws, which are smooth, continuous, and predictable. A 16-minute periodic distortion suggested either a systematic sensor glitch or a real physical force acting on the object, one that came and went in perfect rhythm. The first suspicion was data corruption. ESA's Darmstadt Operations Center sent over the archived telemetry for reprocessing. Nothing changed. The periodic deviation was real. Then they tried solar wind modeling, gravitational perturbations from Mars, even the hypothetical influence of Jupiter. None of it fit. The force required to create such a pattern would have to vary with clockwork precision, something nature simply doesn't do. Meanwhile, independent observatories around the world tried to run their own orbital fits using the publicly available ephemerides. Within days, they realized something unsettling. The numbers coming from official channels had started diverging. The ESA, NASA, and the International Astronomical Union all listed slightly different coordinates for the same timestamps. In most cases, the error margin was small, a few thousand kilometers, but the direction of the offset changed with every cycle. It was as if 3I-ATLAS wasn't moving along a continuous curve, but jumping between predicted positions in increments too small to notice unless you looked closely. At the European Southern Observatory, mathematician Jonas Keller published a private memo describing what he called a fractal drift. In his analysis, the residuals of 3I-ATLAS's trajectory repeated in a self-similar pattern, scaling down by factors of 10 at each interval. "It's like the orbit is folding into itself," he wrote, "as if it's being recalculated in real time." The phrase recalculated sparked heated debate because recalculation implied control. NASA's Orbital Dynamics group tried to simulate the motion using an adaptive algorithm, the same type used to predict spacecraft thrust maneuvers. When they ran the simulation backward, the software solved the trajectory by inserting tiny thrust impulses every 16 minutes. The math was clear. If 3I-ATLAS were applying micro-adjustments equivalent to less than 0.0001 meters per second, the observed anomalies vanished completely. The model fit perfectly. That result was quietly shared with ESA and immediately buried. No public database ever mentioned it. The reason was simple. It implied intent. Something was steering, however gently, a 30 billion-ton object through interplanetary space. The next problem was energy. Even a minuscule thrust requires a source chemical, thermal, or electromagnetic. No known natural process could produce such consistent impulses. And yet, when astrophysicists checked the spectral data, they found faint correlations between the deceleration curve and fluctuations in the solar magnetic field. It was as if the object was using the sun itself as a power source, drawing from it in pulses timed to its 16-minute rhythm. As the calculations piled up, no one could agree on what the numbers meant. The International Astronomical Union, overwhelmed by conflicting reports, postponed all official trajectory updates until further verification. It was the first time in history that an interstellar object's orbital solution was classified as indeterminate. Behind closed doors, mathematicians continued to run models that broke every known rule. Some found that when the 16-minute oscillations were plotted over longer intervals, they mapped into a perfect logarithmic spiral the same curve that defines hurricanes, galaxies, and magnetic flux lines. No one dared publish that. By late October, agencies stopped releasing positional data altogether. The last verified coordinate placed 3I-ATLAS still behind the Sun, though. According to Keller's fractal model, it might have already emerged on a new vector toward the inner solar system. In public briefings, spokespeople continued to reassure that the object remained on a harmless trajectory. But among those who'd run the numbers themselves, a different consensus was forming. The equations weren't broken. They were accurate. The problem wasn't the math. The problem was that something intelligent might be inside it rewriting the math itself. By late October 2025, the tone inside mission control centers across Europe and the United States had changed. The hum of conversation that normally filled the control rooms, the constant rhythm of telemetry, updates, status checks, and muted laughter was gone. In its place was something colder. People spoke in whispers. Monitors were dimmed. The engineers had stopped talking. The first to go silent were the teams at ESA's European Space Operations Centre in Darmstadt. After the lockdown of Vault 9, communication between departments slowed to a crawl. Engineers who once shared calibration notes and troubleshooting logs were told to stop sending emails containing the word Atlas. The justification was framed as cybersecurity protecting sensitive data until verification was nulled. Complete. But inside the control center, everyone knew what it really meant. No leaks. At NASA's Jet Propulsion Laboratory, similar orders arrived a few days later. Project engineers for the Deep Space Network, Mars Reconnaissance Orbiter, and Goldstone Tracking Station were instructed to route all 3I-ATLAS data through a classified server. Even casual internal messages mentioning the object were automatically filtered or deleted. The change was subtle but unmistakable. An invisible wall had been raised between the technical staff and the data they once managed freely. One systems engineer later described it anonymously to a science journalist. It wasn't censorship in the normal sense. It was atmosphere. You'd walk into the telemetry room and everyone would just stop. You could feel that they knew something they weren't supposed to say. By October 22nd, several internal discussion forums used by ESA and NASA engineers for collaboration had gone offline. The official explanation was maintenance, but screenshots circulating among staff showed that the last threads were all about the same topic: questions about the deceleration and the 16-minute light flicker cycle. Within hours, those posts vanished. At the Canberra Deep Space Complex in Australia, a small group of technicians noticed that their automatic data feed from the Goldstone complex had been rerouted to an encrypted channel labelled Level 5, Controlled Dissemination. When they asked for clarification, they received a one-line response: all ATLAS data under centralized review. After that, no one replied to further inquiries. The silence wasn't limited to the agencies. Independent research groups also began losing access to shared databases. The Minor Planet Center, which normally receives public orbital data, stopped publishing updates entirely. Requests for raw signal logs were denied under national security clauses. The effect rippled outward. Astronomers who had built careers on open data suddenly found themselves locked out of their own field. Whispers started to spread among the remaining insiders. Hints of what had been found. Some said the engineers had identified repeating compression patterns embedded in the radar returns from Goldstone, suggesting data encoding. Others claimed that the most recent Doppler readings showed 3I-ATLAS altering its course again, this time accelerating slightly as it moved behind the Sunday. But no one could confirm anything, because no one was allowed to speak. A few tried. On October 25th, a short unsigned message appeared on an encrypted science forum. They think it's responding. Every transmission we send gets one back. Same delay, same frequency, same pulse count. The message was deleted within minutes, but the rumour spread like wildfire. After that, the isolation intensified. Video conferences between ESA and NASA were cut down to pre-approved talking points. All staff were reminded that any public comment on unverified data regarding interstellar objects would be considered a breach of contract. The engineers, the people who built, tracked, and lived with the machines that found 3I-ATLAS withdrew into silence. One technician from JPL, interviewed months later under anonymity, described it this way: "We weren't told to lie. We were told to pause, to stop speculating, stop hypothesizing, stop connecting the dots. But when you're in that room and you see the data, you already know what's happening. You just can't say it." Across continents, silence became the protocol. Communication that had once been open and cooperative now felt like the slow closing of a vault door. Those who had devoted their lives to understanding the universe were now locked out of their own discoveries. For the outside world, the updates ended quietly. Data pending verification, signal under review, telemetry temporarily suspended. But for the engineers, inside those control rooms, the truth was simpler, heavier, and far more personal. They had witnessed something that defied the physics they lived by. And somewhere between curiosity and fear, between discovery and control, every one of them made the same decision. They stopped talking. In the early hours of October 27th, 2025, operators at NASA's Deep Space Network, DSN, noticed something unusual in the logs. Several antennas, including Goldstone's massive 70-meter dish, and its counterparts in Madrid and Canberra had automatically shifted their alignment by fractions of a degree. The reorientation was subtle, barely enough to notice, but it wasn't random. Every dish in the global array had adjusted toward the same coordinates, a patch of sky just east of the sun's limb. At first, it was dismissed as a synchronization error. The DSN's tracking system routinely recalibrates to maintain precise pointing for interplanetary missions, compensating for Earth's rotation and orbital drift. But this was different. The adjustments weren't scheduled. The automatic log entries showed the same triggering code across all three complexes. Auto-lock on external source? That command isn't supposed to exist in normal operations. It's a contingency routine, a safety feature meant to let the antennas lock onto distress signals or unregistered transmitters in deep space. In the DSN's 60-year history, it had never once been triggered simultaneously on all three continents. Within minutes, Goldstone's shift supervisor tried to override the change manually. The antenna ignored the command. The motors continued their slow, silent turn until the dish settled at a precise azimuth, one that, by coincidence or not, corresponded to the predicted re-emergence point of 3I-ATLAS from behind the Sunday. A call was made to JPL's operations center in Pasadena, then to Madrid, then to Canberra. Every team reported the same thing. The antennas had engaged the external source protocol autonomously, using a shared code that no one had entered. When engineers checked the logs, the timestamp of the trigger was identical everywhere down to the millisecond. Inside JPL's Mission Control Building 230, the atmosphere shifted from confusion to quiet tension. Engineers began to suspect an internal breach. The system could, in theory, be hacked, but the DSN operates on a closed network with no outside access. It was more plausible that an external signal strong enough and structured enough had been misinterpreted as a control sequence. That explanation lasted only an hour. By dawn, diagnostic checks confirmed that no false command had been sent from Earth. The trigger had come from space. When analysts plotted the triangulation of the received signal, it pointed squarely toward the sun's far side, the same region where 3I-ATLAS had last been tracked before disappearing. The data packets weren't random noise. They contained structure, repeating binary clusters, uniform intervals, and a modulation depth consistent with artificial encoding. The object hadn't gone silent during conjunction it had been transmitting. By midday, all DSN complexes were placed under passive tracking mode. No active pings, no transmissions, only listening. Each dish began recording continuous raw data, streams hundreds of terabytes per hour, all routed through newly established encrypted channels. The engineers were instructed not to analyze the content locally. Every packet was to be mirrored to a classified JPL archive known internally as Atlas Mirror 1. Outside the agency, the shift didn't go unnoticed. Amateur radio astronomers monitoring the DSN telemetry relays picked up bursts of carrier waves where there should have been silence. In Spain, a retired communications engineer posted online that the DSN dishes are staring straight at the sun for some reason. His post was deleted within hours. Internally, speculation grew. Some believed the reorientation was a failsafe, the DSN reacting instinctively to a strong radio source. Others, less comfortable with coincidences, suspected 3I-ATLAS had initiated the lock itself. The phrasing spread quickly through internal chat rooms before being quietly scrubbed. The object called the network. That night, Goldstone recorded a second pulse, stronger than any before. It wasn't just an echo, it carried phase-coded intervals aligned with the Earth's rotation, as though anticipating where the DSN antennas would be pointing next. The pattern repeated every 16 minutes, then stopped abruptly. Afterward, a senior engineer in Canberra described the feeling in a confidential briefing. It was as if the network was being used against us, like it already knew the rhythm of our own system. By October 29th, the antennas reverted to manual control. The automatic trigger was officially described as a telemetry synchronization fault, but everyone on the inside knew that was impossible. The probability of 3 facilities, half a world apart, receiving the same erroneous activation code at the same millisecond was effectively zero. The DSN had not turned itself. Something out there had called it to attention, and from that moment on, every dish on Earth capable of listening to the stars was pointed at one thing, the space just behind the sun, where a visitor from another system had gone silent and where the first whisper of its return had just been heard. For months, astronomers spoke of 3I-ATLAS as if it were gone, a brief cosmic visitor swallowed by sunlight and distance. But space has its own kind of silence, the kind that doesn't mean absence, only waiting. Now, as the instruments cool and the data streams quiet, every unanswered question remains suspended in that silence. The trajectory that changed, the deceleration that defied physics, the echoes that no one can decode. Across 3 continents, antennas that once reached outward now listen inward, waiting for something that may already be listening back. Perhaps it was all coincidence, solar interference, misread telemetry, human imagination filling the gaps between static. Or perhaps 3I-ATLAS wasn't a coincidence at all. Maybe it was a test, a reminder that discovery doesn't always arrive with light, but sometimes with the loss of it. Somewhere beyond the solar glare, where radiation turns the sky to white, the object still moves unseen, unaccounted for, and still pulsing faintly in intervals of 16 minutes. Whether it's drifting, responding, or deciding its next step, no one can say. For now, the data remains locked, the equations unsolved, and the voices that once spoke about it silent. But silence isn't the end of the story. It's where every signal begins again. This is the moment between knowing and not knowing, the space between 2 transmissions, and when 3I-ATLAS speaks again, if it does, we'll be listening.